I'm Tiffany. Today, I'm going to discuss about escape velocity. What is escape velocity first? Escape velocity usually involves two unequal masses, with the larger mass usually possessing a significant being a planet, star, or moon. For the empiric reason that this larger mass does not rotate a possessed atmosphere in the gravity, only force acting upon the smaller object.
Today, I am going to discuss about escape velocity and Kepler's three laws of planetary motion. But before anything else, may I introduce myself. I am Dibianti Gomez, grade 12 Socrates. So, what is escape velocity? In astronomy and space exploration, the velocity that is sufficient for a body to escape from a gravitational center of attraction without undergoing any further acceleration. Escape velocity decreases with altitude and is equal to the square root of 2 or about 1.414 times the velocity necessary to maintain a circular orbit at the same altitude of the Earth. If atmospheric resistance could be disregarded, escape velocity would be about 11.2 km or 6.96 miles per second. The velocity of the escape from the less massive moon is about 2.4 km per second at its surface. A planet or satellite cannot long retain an atmosphere if the planet's escape velocity is low enough to be near the average velocity of the gas molecules making up the atmosphere. In physics, specifically celestial mechanics, escape velocity is the minimum speed needed for a free, non-propelled object to escape from the gravitational influence of a massive body. For a spherically symmetric, massive body such as a star or planet, the escape velocity for that body at a given distance is calculated by the formula. Escape velocity is equal to square root of 2 gm all over r, where g is the universal gravitational constant, which is equal to 6.67 times 10 to the power of negative 11 cubic meter times kilogram to the power of negative 1 times s to the power of negative 2. M is the mass of the body to be escaped from, and r is the distance from the center of mass of the body to the object. Here is the example. The radius of Earth is 6.38 times 10 to the power of 6 meter, and the mass is 5.96 times 10 to the power of 24 kilogram. What is the escape velocity from Earth? So, the escape velocity of the Earth can be found using this formula. Escape velocity is equal to the square root of 2 gm all over r. So, the solution is escape velocity is equal to the square root of 2 times the gravitational constant, which is 6.673 times 10 to the power of negative 11 Newton times meter squared all over kilogram squared, times the mass of the Earth, which is 5.98 times 10 to the power of 24 kilogram all over the radius of the Earth, which is 6.38 times 10 to the power of 6 meter. So by using the scientific calculator, you will get the answer. The escape velocity of the Earth is equal to 11,184 meter per second, or approximately 11.2 kilometer per second. Topic is about Kepler's three laws of planetary motion. So in astronomy and classical physics, laws describing the motions of the planets in the solar system. They were derived by the German astronomer Johannes Kepler, who is the assistant of Tycho Brahe, a prevalent astronomer who worked before the invention of the telescope, and whose analysis of the observations of the 16th century Danish astronomer Tycho Brahe enabled him to announce his first two laws in the year 1609 and a third law nearly a decade later in 1618.
Kepler's law of planetary motion. Kepler's first law. The orbits of the planets are ellipses with the sun at one focus of the ellipse. There is no object at the other focus of the planet's orbit. The semi-major axis A of an orbit is the average distance between the planet and the sun. As a planet travels in its elliptical orbit, its distance from the sun and speed vary. A planet moves most rapidly when it is nearest the sun or at perihelion. A planet moves more slowly when it is the farthest from the sun or at aphelion. Kepler's second law. The line joining the planet to the sun sweeps out equal areas in equal times as the planet travels around the ellipse. This is also known as the law of equal areas. Suppose a planet takes 1 day to travel from point A to B. During this day, an imaginary line from the sun to the planet will sweep out an area. The same area will be swept every day. Here, the areas A1 and A2 are equal and the time T1 and T2 are also equal. Kepler's third law. The ratio of the squares of the revolutionary periods for two planets is equal to the ratio of the cubes of their semi-major axis. T square is directly proportional to R cube. So, T square by R cube is equal to Kepler's constant.
That's all. See you next time.
Annyeonghaseyo! Daghang salamat!